By the end of 2025, a new analysis posted to arXiv surprised the astronomy community. The team led by Joseph Trio Rodriguez reported that the spectrum of 3I Atlas looked almost identical to carbonaceous chondrites, the ancient mix of carbon, water, and heavy metals found in some of the oldest meteorites in the universe. These materials usually stay locked inside cold, inactive fragments drifting through space, but this time they were coming from an object that was brightening as it moved toward Earth. The unexpected part was not the composition alone, it was the behavior that followed. Instead of fading, 3I Atlas continued to strengthen its glow, showing signs of activity that did not match something made from primordial dust. Its light curve shifted in small but consistent ways, as if the object were pushing against its own path. If 3I Atlas truly carries the earliest material in the cosmos, then why does its behavior resemble something waking rather than something ancient? Carbonaceous chondrites are rare visitors in our solar system. They carry iron-nickel grains and frozen water locked inside a dense primitive mix that barely changes over billions of years. Most comets here do not contain this combination, and the few that do never show strong activity. That is why the signature detected on 3I Atlas immediately set it apart. Its light did not resemble the comets cataloged in our telescopes. It pointed to a place of origin unlike anything we have mapped before. If the spectrum is correct, then 3I Atlas may have formed in a system far older than our own, one shaped during the early stages of the Milky Way. Material like this usually belongs to stars that lived and died long before the Sun existed. It suggests that the object's journey spans distances and timescales far beyond the comets that drift inside our neighborhood. And yet, despite its ancient composition, 3I Atlas behaves nothing like a relic from deep time. The arXiv study also raised a possibility that pushed the mystery even further. Some of the compounds detected in the coma could be the result of metal-ice reactions occurring inside the nucleus. These reactions are rarely discussed outside scientific circles because they do not appear in typical comets. But if iron, nickel, and frozen water interact under certain pressures, they can produce unusual gases that escape into space. This process has no confirmed natural example in our solar system. Seeing hints of it here challenges the assumptions about what an interstellar object can do. The question is not only where 3I Atlas was born, but what it is doing right now. If reactions inside the core are active, then the object is not simply reflecting sunlight, it is changing itself as it moves. None of this matches the behavior of the quiet, carbonaceous bodies we have studied before. Those remain dark and stable. 3I Atlas, on the other hand, shows signs of internal activity that should not exist in something so old. That leaves a mask hanging over the object. 3I Atlas does not just carry ancient material. It may be generating reactions with no precedent in comet science. Something inside it is producing compounds that do not fit the models we use for icy objects entering the inner solar system. And if that is true, then the origin story of 3I Atlas is only the beginning of the mystery, not the end of it. When the first amateur images of 3I Atlas appeared online, most observers expected a faint point of light, the kind that usually marks a distant comet with a dark, carbon-rich surface. Instead, they found something far brighter than anyone predicted. The nucleus of 3I Atlas reflected light with an intensity that did not resemble the muted glow of typical comets. It stood out sharply even in small backyard telescopes, hinting that its surface was nothing like the black, powdery crust found on most icy bodies drifting toward the Sun. For a comet made from primordial material, this was unexpected. If its core contains a high concentration of metals, as suggested by the spectral readings, the reflectivity could jump far beyond the average 4% seen in dark carbonaceous comets. Metals scatter sunlight more efficiently, and if the surface is fractured or uneven, the brightness can increase even more as different angles catch and return the light. Amateur measurements across multiple nights showed the same pattern. 3I Atlas remained consistently bright, refusing to dim the way most inbound comets do when dust begins to spread out. The coma only deepened the mystery. It stretched nearly 17,000 kilometers across, wide enough to envelop Earth entirely. A coma that large means one of two things. Either the nucleus is unusually active, releasing dust at a rate far higher than expected, or the material surrounding it is structured in a way we do not yet understand. The brightness inside that massive shroud did not decline smoothly. There were pockets of light that seemed to shift, brighten, and fade with a rhythm that did not align with a single solid nucleus rotating in space. That brought observers to a surprising possibility. What if the intense glow was not coming from one reflective core at all? What if the light was bouncing off thousands of small fragments, traveling with the object, each reflecting the sun like tiny mirrors? A debris cloud made of metal-rich particles could behave this way, amplifying the overall shine and making the comet look far more luminous than it should. It would also explain why the light curve showed subtle irregularities, the kind that appear when multiple objects contribute to a single beam of reflected sunlight. If this is true, then 3I Atlas may not be presenting a single face to us. It might be revealing an entire swarm moving as one, a cloud of ancient material scattering light across space. And if the brightness we see is the combined signature of many pieces rather than one core, then the structure of 3I Atlas is more complex than any comet we have ever tracked. Reports from Space Tracker and the amateur community began to show a pattern that caught researchers off guard. 3I Atlas was not just active. It was erupting with a force that pushed it far outside the range of typical comet behavior. The coma thickened week after week, becoming denser, brighter, and more chaotic as new material billowed outward. Instead of settling into a steady plume, the surrounding cloud kept expanding, as though something deeper inside the object was releasing energy in sudden bursts. Forward jets became the next unexpected clue. These high-speed streams of gas and dust extended in front of the comet's direction of travel rather than behind it, breaking the simple picture of sunlight heating one side and causing material to escape. Alongside them were microjets flickering in and out around the nucleus, appearing on a repeating schedule. Amateur observers comparing timestamps began noticing the same cycle. The jets brightened at regular intervals, dimmed, then returned again. This was not the random sputtering of a melting comet. It looked organized. Such behavior is usually associated with hypervolatile activity, the kind seen in objects loaded with CO2 or other materials that react violently when exposed to sunlight. But even that explanation raised new questions. Hypervolatile bursts are usually short-lived. They spike, release energy, and fade. 3I Atlas, by contrast, kept producing fresh jets as if some internal reservoir was being renewed rather than depleted. Its long exposure to interstellar radiation might explain the presence of trapped volatiles, but it did not explain the rhythm. The more the data accumulated, the stranger the picture became. If the interior of 3I Atlas is packed with CO2 ice, then the jets should vary with distance from the sun, changing as temperatures rise. Yet the activity levels seem tied not to temperature but to motion, appearing at nearly the same rotational phase each time. It was almost as if the comet were turning a dial, releasing energy in pulses that matched its spin. This opened the door to a deeper twist. If the bursts were not simply the result of natural heating, then what mechanism was setting the timing? What locked the jets into a repeating schedule that behaved more like a clock than a melting surface? The eruptions could still be natural, driven by pressure building beneath a fractured crust. But the problem remains. Nature rarely keeps time this precisely. And if 3I Atlas is not counting the seconds, then something inside it is. The first hints came quietly, buried in a routine data release. NASA confirmed that one of its newest satellites, Punch, had captured 3I Atlas and Mars in the same frame between September 20th and October 3rd. At first glance, it sounded like a simple alignment, the kind that happens when objects drift across each other's fields of view. But when analysts pulled still frames from the sequence, something far more unusual appeared. The coma of 3I Atlas stretched across the image with such a large angular size that it blurred the edge of Mars itself. For an interstellar object still far from its closest approach, this was remarkable. Comas do not usually appear this large at such distances, and they certainly do not obscure an entire planet's outline. Yet frame after frame showed the same thing. Mars looked like it was being seen through a soft haze, while 3I Atlas glowed with a scale and sharpness that exceeded expectations. Amateur astronomers who reviewed the images said it looked less like a background comet and more like a foreground object expanding at an unusual rate. Despite the scientific value of a moment like this, almost none of it appeared in NASA's main press briefing. The event was summarized in a single line, treated as an incidental alignment rather than a milestone. There was no discussion of the angular size, no mention of the coma overpowering the planetary boundary, and no follow-up explanation about why the visibility was so strong. The omission immediately drew attention. For a discovery this rare, the first documented image of an interstellar comet and Mars captured simultaneously, the silence felt out of place. Soon the questions began circulating across astronomy forums. Why was a unique observational moment not highlighted? Why avoid discussing an image that could help scientists calculate the coma's true expansion rate? And why release the frames quietly without the usual context that accompanies significant findings? Even professional researchers admitted they expected NASA to emphasize the overlap, not downplay it. That subtle mismatch created the twist. If this was the only time in history that an interstellar object and a nearby planet appeared together in a calibrated observation, why wasn't it treated as a breakthrough? What made the agency speak cautiously about something so visually striking? There may be practical reasons, incomplete analysis, uncertain calibration, or a desire to avoid early speculation, but the absence of emphasis left room for doubt. And once that doubt appeared, a simple question followed. If the moment mattered so little, why did it look so extraordinary? When JPL's Horizon system updated its orbital solution for 3I Atlas, researchers noticed a shift that could not be accounted for by gravity alone. The object was drifting off its predicted path by a small but persistent amount, the kind of deviation that signals a non-gravitational force at work. This phenomenon has been seen before, most famously with 1I/Oumuamua, but the scale documented for 3I Atlas was stronger and far more difficult to explain. Instead of a subtle nudge, the data suggested a continuous push, almost as if an active force was operating inside the object. Normally, comets experience mild non-gravitational acceleration when sunlight warms their surfaces and gas escapes in uneven bursts. But for 3I Atlas, the numbers did not match standard outgassing behavior. The acceleration did not correlate cleanly with its distance from the sun, and it remained stable even when its brightness fluctuated. That stability complicated the picture. Outgassing tends to be messy, unpredictable, and tied to temperature. Whatever was influencing 3I Atlas seemed more controlled. One idea raised by the arXiv study is that metal-ice reactions inside the nucleus could create internal pressure unlike anything seen in typical comets. Iron and nickel trapped in ancient water ice might release unusual gases if exposed to cracks or changing temperatures. These gases could exit through narrow vents, creating a directional force strong enough to push the object slightly off course. It is plausible, at least in theory, but such reactions have never been observed in an interstellar object before. Without a direct sample, scientists can only propose mechanisms based on the signatures in the coma. Still, the internal reaction model runs into a familiar problem. If the pressure were random, the acceleration should wobble as different vents open and close. But the drift of 3I Atlas remained oddly smooth across multiple measurements. Amateurs comparing ephemeris updates found the same trend. The object kept moving as though something steady was giving it a consistent push. That opened the conversation to a far more provocative possibility. What if the force did not come only from inside the nucleus? What if it came from a structure we have not yet seen? Perhaps a cluster of fragments, or a distributed mass that behaves differently from a single solid core? If 3I Atlas is surrounded by reflective particles or shaped by an internal network of cavities, even subtle pressure changes could create a unified direction of thrust. It is not evidence of anything artificial, but it is evidence that we do not yet understand the source of the acceleration. And until we do, a simple question lingers. Is the force pushing 3I Atlas a quirk of chemistry or the signature of a structure still hidden from view? The next clue came from a shape no comet should normally display. When astronomers examined the recent images, they noticed that 3I Atlas had developed a distinct anti-tail, a narrow stream of dust pointing toward the sun instead of away from it. Under ordinary physics, this is not how comet tails behave, but a theoretical model proposed by Avi Loeb offered a possible explanation. If an interstellar object is shedding a cloud of small fragments, those particles can drift inward under solar radiation pressure, forming an anti-tail that aligns precisely the way 3I Atlas now appears on cameras. The surprising part was how cleanly the model matched reality. Observers compared images taken weeks apart and found the same sharp structure stretching sunward. It did not fan out like gas. It looked organized, narrow, and consistent, a sign that the particles composing it might share similar sizes and reflectivity. That pattern pushed the discussion in a new direction. Instead of asking why 3I Atlas was brightening, researchers began asking whether the brightness was being multiplied by an entire population of fragments traveling alongside it. The Hubble Space Telescope added weight to the idea. Recent photometric readings showed scattered light that hinted at many small reflective grains, the kind that would behave like a coordinated cloud rather than isolated debris. Yet even Hubble could not determine how many pieces were present. The reflections were too blended, their signatures overlapping as they moved in near-perfect formation. To some analysts, this was a sign of natural shedding from a fragile nucleus. To others, it looked like the remnants of a structure coming apart or reorganizing over time. What made the situation more intriguing was the scale. A cloud of fragments large enough to create a visible anti-tail would have to be significant in number, and their reflectivity would have to be unusually high to match the sharpness seen in the images. That aligned uneasily with earlier observations of 3I Atlas being brighter than expected, as though the nucleus was not the only source of reflected sunlight. If the object was carrying a field of particles around it, the fragments could be amplifying its luminosity and even affecting its motion. This brought the chapter to its central twist. These fragments may be natural, pieces broken from an ancient metal-rich core after countless cycles of pressure and radiation, but the possibility remains that they were produced by 3I Atlas itself, not by decay, but by an internal process we still do not understand. If the cloud is self-generated, then 3I Atlas is not just breaking apart, it is reshaping itself in real time. The countdown now moves toward a moment astronomers have been anticipating for months. On December 19th, 3I Atlas will reach its closest approach to Earth, passing near enough for telescopes to capture high-resolution data on its jets, its anti-tail, and the cloud of fragments that may be traveling with it. For the first time, we will be able to see the behavior of the object not through distant smears of light, but through detailed frame-by-frame measurements. Every burst, every shift in brightness, and every pulse of material will be tracked with unprecedented clarity. If the activity we have witnessed so far is only the beginning, this encounter will make it impossible to ignore. But the true test comes after the Earth passes. As 3I Atlas continues outbound, it will enter the gravitational domain of Jupiter, a region where deviations in motion are impossible to hide. Jupiter's pull is strong enough to expose even the smallest irregularities in an object's trajectory. If 3I Atlas is being pushed by non-gravitational forces, the giant planet will reveal it. The slightest unexplained acceleration will stand out against the predictable curves drawn by Newtonian mechanics, allowing scientists to determine whether the object is drifting by chance or being driven by something structured. This stage of the journey matters because it separates unusual comets from something entirely different. Most comets show chaotic outgassing that fades with distance. 3I Atlas has done the opposite. Its activity has strengthened, its jets have synchronized, and its brightness has become increasingly difficult to explain with natural models. If the non-gravitational acceleration continues as it moves beyond Earth, maintaining the same direction and magnitude, then the object no longer fits into any known category. It stops being an anomaly and becomes evidence of a new class of interstellar body, something with internal processes that behave unlike anything we have previously tracked. And that leads to the chapter's central question. Jupiter is not just a bystander in this story. It is the solar system's most powerful lens, capable of revealing what 3I Atlas has been hiding behind, shifting light curves and expanding comas. As the object crosses into Jupiter's influence, every irregular push and every fragment working in formation will become visible through its motion. This is the phase where the mystery can no longer disguise itself. If something inside or around 3I Atlas is guiding its path, Jupiter will expose it. The only question now is whether the giant planet will confirm a strange comet or uncover something far more unfamiliar. Across months of observation, a single truth has become impossible to ignore. 3I Atlas is not behaving like a normal comet, and each new piece of data only widens the gap between expectation and reality. It carries the spectral fingerprint of primordial material, the same ancient mix found in meteorites older than the planets themselves. Its jets erupt with hypervolatile force, refusing to fade even as it moves through regions where most comets grow quiet. And instead of absorbing sunlight like the dark, carbon-rich surfaces we know, its nucleus reflects light with the brightness of metal. These are not isolated anomalies. They are interconnected signs of an object that does not fit the rules. Then comes the anti-tail, a thin, sunward streak that matches models predicting the presence of drifting fragments. Observations from Hubble show scattered light that behaves as though many small reflective pieces surround the object, though no one can count them or determine their exact size. Combined with the oversized coma and the rhythmic jets, the debris cloud paints a picture of a body that may be shedding, restructuring, or interacting with sunlight in ways no comet has demonstrated before. Yet perhaps the clearest signal that something unusual is happening lies in its motion. The non-gravitational acceleration recorded in JPL's Horizons database shows a persistent push acting on 3I Atlas, strong enough to shift its path, but stable enough to suggest a mechanism more consistent than random outgassing. Scientists have seen slight deviations in comet trajectories before, but not at this scale and not with this degree of consistency. Whatever force is at work here is subtle but steady, leaving its mark on every updated orbital calculation. Taken together, the primordial material, the hypervolatile eruptions, the metallic reflectivity, the anti-tail, the drifting fragments, and the unexplained acceleration. These clues converge into a single puzzle. 3I Atlas may be the most complex interstellar object ever observed, a visitor whose behavior challenges the frameworks used to understand bodies from beyond the solar system. The mystery is not simply that the object is old, it is that the object appears to be changing, adapting, or revealing new characteristics as it travels deeper into our neighborhood. So the final question remains: if 3I Atlas is not just a remnant of ancient cosmic history, but something transforming in real time, what exactly are we witnessing as it moves past Earth and into Jupiter's domain? Share in the comments which feature of 3I Atlas strikes you as the most unusual, and why you think this interstellar visitor refuses to behave like anything science has seen before.